Hi guys, welcome to a new video. Today we are going to find the electric field produced by a uniformly charged line segment. The problem says find the electric field at a distance z above the midpoint of a straight line segment of length 2L that carries a uniform line charge lambda. So the illustration for this problem is this one. So we have here this illustration that shows you the line segment that is charged. So we have here the line segment lying on the x-axis. This is x equals 0. And the line segment extends from x equal minus L to x equal L. This is x equals 0. Okay. The bar has uniform charge density lambda, and we want to find the electric field at the point P right here. The point P is located at a distance z above the center of the line. The observation point on the z-axis is on the z-axis, so its position vector is r. So we will call the position vector from the center, let's say the center of the bar to the point P. Let's call that position vector r. And because the distance between the center of the line and the point P is z, we can write that position vector like r is equal to z pointing to the z direction, right? So we write the unit vector along the z direction. Now we want to take a small piece of charge somewhere on the line, okay? Since the line lies on the x-axis, the position of this small charge element is x. So it's right here. This x is the position from the origin, x equals 0, to the point where the element of charge is. I selected the element to be this one. The position from the origin to that charge element is, let's call it r prime, and that's equal to x along the x direction. Okay, so you can see this vector position r. This is the x r prime. Okay. Okay, according to the geometry of the problem, we can write that r minus r prime. Okay, according to the geometry of the problem, we can write that. So if we substitute the two position vectors, we will be able to write this position from the element dx to the point P like z along the z direction minus x along the x direction. Okay. This vector is important because Coulomb's law needs the direction from the charge element to the point where we are calculating the electric field. So the magnitude of this vector is, as we should know, is r is equal to the root square of x squared plus z squared. We can write the unit vector like this. Our unit vector is equal to the r vector dividing its magnitude. Okay? Because we can do that, we will have something like, remember, we already wrote the r position like this through the vector positions. We can write something like this, just replacing. We can write something like z to the z direction minus x to the x direction, dividing the magnitude of this vector that is from the previous equation, x squared plus z squared. So this unit vector will tell us where the direction of the electric field that is produced by this element dx is pointing to. Okay? Now we want to define the small charge element. We remember that we said that the charge density is lambda. This charge density is the charge per unit length. So if we see the illustration, we will see that here we have the element dx right here. Okay, that element dx will have a charge density as well. So a small piece dx will contain charge dq equal to lambda dx. Okay, so this is from the definition. We said that lambda is charge per unit length, but because we are talking about the differential element of charge, the differential element of charge is dq and its length is dx. So from this definition we have this. The key idea is this: instead of treating the rod as a one object, we want to divide it into tiny pieces dq, and find the total field from each one, adding them up, and that way we can find the electric field for the whole bar or for the whole rod. So now we want to apply the Coulomb's law to this system. For definition, we have the following. For a small charge element dq, Coulomb's law gives the E equal to 1 dividing 4 pi epsilon 0 dq dividing r squared along the r direction. So if we go to the illustration, we will see I will change a different color. Let's say again this is the dq element. We already know that the q element has length dx, so I just want to say that this is the q again, and the unit vector pointing to the point P where we are calculating the electric field is this. Okay, and we want to say the electric field produced by this element dq at this point P, by definition of the Coulomb's law, is this. Okay, we already know that. So because we know that lambda is dq equal lambda dx, we just replace this into this equation and we get something like this. Okay, we get something like that. So now we substitute the expression for r into this equation, and we will get something like this. dE is equal to 1 dividing 4 pi epsilon 0 lambda dx dividing s squared plus z squared. Multiplying z along the z direction minus x along the x direction, dividing root square of s squared plus z squared. What I did here is just replace r squared by s squared plus z squared. So it's the same expression, but it's as a function of x and z, because we already have those expressions here, so we want to do some algebra with them. So that's why I just replace it. Okay, so now we can write this equation like dE is equal to 1 dividing 4 pi epsilon 0 lambda dx. So here we get this with this. It's going to be x squared plus z squared to the third half power. Here we have z along the z-axis minus x along the x-axis. Okay, so now we want to integrate over the entire line. So the line goes from minus L to L, and we want to integrate this expression, okay? And we use minus L and L as the limits of integration. So we get E is equal to lambda dividing 4 pi epsilon 0. You know, these terms don't go into the integral because they are constant. This is the integral from minus L to L, z minus x dx dividing s squared plus z squared to the 3/2 power. That's beautiful. Now we are going to separate the z component from the x component, and we will get something like this. So what I did here is I just wrote the components of each term separate, and these two terms they go out of the integral because the integral is a function of x, right? Here I take out of the integral the unit vector because basically it's a vector, right? So we want to just have the integral as a function of x, as we can see here. So now we have these two components for this integral. Here is where the physics becomes clear. So let's talk about each component right now and see what happens. The first integral is this, and nothing is weird with this, so we will solve this integral. And the second integral is this. Now we see the second integral. The second integral gives the horizontal component, but the rod is symmetric. So for every charge element at x, let's say we have a charge element at x, we will have another charge element at minus x. And those components, they will cancel each other. So let's go to the illustration real quick and see what is happening. If we see, let's say, this component, we are seeing this component right now. And the x component of the field for this component right here is this. Okay, this vector pointing to the left. So we will have a symmetric equal component right here. And that symmetric equal component will have a component for the electric field pointing to the right. So these two components, they will cancel each other. And the same will happen with all the components along the rod. So that's why the x component of the integrals becomes 0. Then we will have that. So let's keep working on the first integral, that is the only one that is surviving. Then we will have E is equal to lambda z dividing 4pi epsilon 0, 4pi epsilon 0, integral from minus L to L dx dividing s squared plus z squared to the 3/2 power. Okay, that's what we have. So that comes from here. This is the only component that is surviving. Okay. Okay, guys, let's solve this integral, and we will use trigonometric substitution to solve this integral. So we go like, let's write the integral. The integral is integral of x dividing z squared plus x squared to the 3/2 power dx. Let's do trigonometric substitution. To do the trigonometric substitution, we just draw a triangle. We have an angle theta right here. This is z, and this is, according to this triangle, we will have the tangent of theta. Tangent of theta is equal to the opposite side, that is x, dividing the adjacent side, that is z. Okay. We will have then that x is equal to z tangent of theta. Okay. And why we do this kind of substitution? Remember, we have the rod, right? Remember, we have the differential chart here and the point P here. So we are using the same geometry. And remember that we have the positions of the position of this element with respect to the origin, right? So that's why we are using this triangle, because it has the same geometry of the problem. Okay, so we have the x is equal to z tangent of theta. Then we differentiate this expression, and we will have dx d theta is equal to derivative of tangent of theta is secant square of theta. We have z here. Then we can write dx is equal to z secant square of theta d theta. Now we have the denominator of the integral right here, and it is z squared plus x squared. Okay, that's equal to z squared, right, is this term, plus x squared, this term, but this term is this term. So we write z squared tangent squared of theta. Then we can write it like this: z squared plus x squared is equal to, we take factor out of z squared equal to 1 plus tangent of theta. Okay, now we use identity. Remember the identity: tangent square of theta plus 1 is equal to secant square of theta. So we replace that identity here. And when we replace that, we get x squared plus z squared is equal to z squared secant square of theta. Okay. Remember that the denominator of the integral is this: z squared plus x squared to the 3/2 power. So we write here, then this is going to be equal to z squared secant squared of theta to the 3/2 power, because this, right? So if this is equal to this, then this to the 3/2 is equal to this to the 3/2. So that's something that is pretty easy to see. Now we simplify this expression, and then we will have something like x squared plus z squared to the 3/2 is equal to, okay, I just going to write it again and simplify here to see what's going on. So this square is going to simplify with this half, and this square is going to simplify with this half as well, right? So because of that, we will get s squared plus z squared to the 3/2 is equal to z to the 3rd power multiplying secant to the 3rd power of theta. Now we will substitute this expression into the integral, into the original integral. So we get integral of the x dividing s squared plus z squared to the 3/2 is equal to the integral of the x, right? But the x, remember, the x is equal to z secant square of theta d theta, right? Dividing s squared plus z squared to the 3/2, and that is equal to the z cubed multiplying secant to the 3rd power of theta. We simplify this as much as we can. We just, this one simplifies with this, and this simplify with this, and we will get something like integral of d theta dividing z squared secant of theta. Okay. Now we have another trigonometric identity. 1 dividing secant of theta is equal to cosine of theta, right? So we get that the integral is going to be integral d theta dividing, we take the z squared out of the integral, sine secant of theta. This is going to be 1 dividing z squared integral of cosine of theta d theta. This is pretty easy. because the integral of cosine of theta is sine of theta. Then, when dividing z squared multiplying integral of cosine of theta d theta is equal to 1 dividing z squared multiplying sine of theta d. Okay, that's it. Now we return to the original variable. Returning to the original variable, we get something like, we remember that the original variable is x equal to z tangent of theta, right? And do you remember that we had a right triangle? A right triangle is this. We already have it, but I am drawing it real quick. So this expression comes from here, okay? But from the last integration by trigonometric substitution, we got that the integral, let's call it I, is equal to 1 dividing z squared sine of theta. But if we go to this triangle is sine of theta is equal to the opposite side dividing the hypotenuse. The hypotenuse is root square of s squared plus z squared. Then we can write the integral like I 1 dividing z squared multiplying x dividing root square of s squared plus z squared. Okay, guys? Then the integral dx dividing s squared plus z squared to the 3/2 is equal to x dividing z squared multiplying s squared plus z squared. That's the result of the integration by trigonometric substitution. So now we remember that the electric field is equal to E equal to lambda z dividing 4 pi epsilon 0 integral from minus L to L dx x squared plus z squared to the 3/2 z direction. What we have to do is to replace this result into this expression of the electric field. Okay? So if we do that, we will get something like this. Okay? Now we just replace the integration limits from L to minus L. So if we substitute the upper limit, the integral will look like this. And if we substitute the lower limit, we will get. So now when we subtract the lower limit from the upper limit, as you see here, these two signs, minus and minus, they become positive when we multiply them, and these two terms, they are equal, so we get 2 times L dividing z squared multiplying root square of L squared plus z squared, right? Finally, the integral from minus L to L of this expression is equal to 2L dividing Z squared root square of L squared plus Z squared. Finally, we can substitute this expression into the electric field expression. So the electric field expression, remember, is E equal to lambda Z dividing 4 pi epsilon 0. Okay, remember here we have the integral, right? We already substitute the limits and we got this. And this goes here. 2L dividing Z squared multiplying root square of L squared plus Z squared in the Z direction. Simplify this expression, please, with this. Simplify. And the final answer for the electric field is. And that's the final electric field. As you see, the direction of the field is along the Z direction. And it's given by this unit vector. Because the charge is positive in this case, and the observation point is above the line. Okay, so this is the expression for the electric field. So we can take into consideration some situations. So let's say that the observation point is far away from the bar, right? And that means that Z is much higher than L. So P is too far away. When that happens, we will have that root square of L squared plus Z squared is approximately equal to Z, right? So then the field becomes E approximately equal to 1 dividing 4 pi epsilon 0 to lambda L dividing Z squared. Okay? And that would be the electric field when Z is much higher than L. Okay? And that happens when this is the situation. Remember, the total charge is going to be Q. It's going to be like the density, lambda, multiplying the distance, the length of the rod, and the length is to L. We can replace this expression right here too, and we can get something like this. E equal to, or approximately equal to 1 dividing 4 pi a0, and this is going to be Q dividing Z squared along the Z axis. Okay? Remember, the charge is the definition of the charge is density multiplying length, and we replace this here and we get this. And what is this? This is exactly the field of a point charge. Okay, so this result makes physical sense. This is for a point charge because the observation point is too far away. Where we see from the observation point, where we see is just a point charge where the on the location where the bar is. So this is the problem that I wanted to solve with you guys on this occasion. If you like my content, just give me a like, subscribe to my channel. You can also share this content with your friends at the school to study together. And see you on the next video. Thanks for watching.